We present perception control coupled visual servoing, a novel keypoint-based extended Kalman filtering approach that improves the robustness of visual servoing for textureless objects. Classical visual servoing approaches, such as image-based visual servoing and pose-based visual servoing, all rely on handcrafted features to estimate either the image Jacobian or object pose to compute the final velocity control output. However, textureless objects often lack distinctive features. This makes computing feature correspondences unreliable, ultimately leading to performance degradation. With advances in deep learning, many methods have been developed to leverage learning-based feature extraction and integrate them with an IBVS controller, or alternatively, directly estimate the 6D object pose to incorporate it with a PBVS framework. In our work, we adopt PVNet as our keypoint-based pose estimator. While we use PVNet, other keypoint detection methods also work as a drop-in replacement. For the PVNet plus IBVS baseline, we use PVNet to first extract object keypoints. The keypoint correspondences are then used to compute the control velocity following the IBVS control scheme. For the PVNet plus PBVS baseline, we again use PVNet to first extract object keypoints, but also use them to fit a 6D object pose. This pose is then used to compute the control velocity using PBVS. However, solely relying on visual features results in brittle detections under adverse conditions. Here, both baselines produce erratic control velocities under rapid illumination changes. To address these issues, we present perception control coupled visual servoing, tightly coupling both perception and control information to enable robust visual servoing in adverse conditions. First, we use PVNet to acquire per-frame object keypoints along with their associated uncertainties. We then use the EKF to fuse keypoint measurements with the previous control velocity as a motion prior to output a more reliable 6D object pose. This pose is then used by PBVS to compute the velocity command, while the a posteriori pose uncertainty is propagated to regulate the control velocity, which together reduces erratic unsafe motions. Finally, the executed velocity is used to update the motion prior, and the new object keypoint measurements are acquired again using PVNet, closing the perception control couple loop. Deploying our method on a Franken manipulator platform, we demonstrate that our method servos with textureless objects while being robust to different visual backgrounds. Here, our method also successfully servos to the desired position for the textureless object while remaining robust to occlusions. Finally, our method performs smoother, safer trajectories despite severe image feature degradation on the textureless target objects under erratic lighting conditions. We further demonstrate our approach in a robotic grasping application. Here, our method is used to servo to a desired pose near the object of interest. Once the pose is reached, a pre-computed motion offset is then executed, allowing the robot to grasp the object. We observed that our method consistently achieves smoother trajectories and more accurate final poses across all textureless objects under adverse conditions, resulting in the highest success rates compared to all our baselines. Thanks for watching.